So first, let me give an outline of my talk. I'm going to tell you about a model that came from biology and traffic flow called the asymmetric simple exclusion process, or ASEP. And then I'll tell you about how one can answer questions about the ASEP using some combinatorial objects. I'll then explain a generalization of this model and corresponding combinatorics. And finally, I'll tell how everything is tied into some orthogonal polynomials. Okay, so let's talk about traffic. So let's consider a one-way road. We're going to keep things simple, with cars entering at one end and exiting at the other. Now, one would like to understand the behavior of traffic in this sort of simple situation, addressing questions like current, how many cars move past one spot in unit time, density, what's the average number of cars present, distribution, what's the probability that we see a particular configuration of cars. There's a picture of traffic on a one-way road. Okay, so now let me get a little bit more mathematical. This is still on this slide not a precise mathematical definition, but it's getting there. So we're going to fix a one-dimensional lattice of n sites. In this picture, n is equal to 6, and every site can be either occupied by a particle, car, or it can be empty. And we're going to choose some parameters that govern hopping rates. So at the boundaries of the lattice, new particles can enter and exit the lattice from the left at rates alpha and gamma. Particles can exit and enter from the right at rates beta and delta. Of course, on a one-way street, one would hope that gamma and delta are 0, but let's keep things, allow ourselves the flexibility for the moment. Particles can hop right at rate 1 and left at rate q, and it's asymmetric in that we don't require q to be equal to 1. The word exclusion in asymmetric simple exclusion process refers to the fact that there's at most one particle on each site. You don't want two cars on top of each other.
So in this one-way street, they can actually back up? Is that?
Well, we're allowing that in our model, but one would hope that q, gamma, and delta are 0.
But these are not the probabilities, right? Because you have one of them is 1.
That's right. So they're not, at this point, they're not yet probabilities, but they're rates. But I'll make everything precise as a Markov chain in a moment. So particles I will depict as black circles or 1, and holes will be circles or zeros. And a basic question is, well, what happens as time goes to infinity? What kind of distribution do you expect? Okay, so to back up, so where did this model come from? It was actually introduced by biologists in 1968. They were trying to come up with a model for translation and protein synthesis. And more or less at the same time, it was introduced independently by a mathematician, Spitzer. There's been an enormous amount of study of this model by many people. This is a very incomplete list. Last time I checked, there were 1,000 papers on the exclusion process on the archive. Okay, so now I'm going to give the formal mathematical definition. So B sub n is the set of all 2 to the n words of length n on letters whole and particle. And then the ASEP is the Markov chain on the state space B sub n with the following transition probabilities. So here, x is an arbitrary word. So A and B you should think of as arbitrary words in wholes and particles. And what I'm trying to depict in this word is that there's a particle somewhere in the middle with a hole just to its right. Now y is exactly the same state, except that hole and particle in the middle have swapped places. And in this case, the probability of going from x to y is 1 over n plus 1, and the probability of going back the other direction is q over n plus 1. Now, if x is an arbitrary word with a hole at the far left, and y is the same word, but that hole has been replaced by a particle, then the probability of going from x to y is alpha over n plus 1, and of going back the other direction is gamma over n plus 1. And then similarly, if x is a word with a particle at the far right, and y is the same word, but that particle has hopped out, the probability of going from x to y is beta over n plus 1, and of going in the other direction is delta over n plus 1. And in any other situation, the probability of going between two distinct states is 0, and the probability of staying in the same place is exactly what it has to be, namely 1 minus the sum of the probabilities that one exits from that state. Okay, so here's a picture when n is equal to 2. We have 2 to the 2 different states, which are depicted here. Whoops. And the arrows show all of the different transitions among the states. And I also have these self-loops. So that self-loop represents the probability of staying in the same place, and that number should be 1 minus gamma over 3 minus delta over 3, minus 1/3. Okay, so people in statistical mechanics are interested in this model because, for example, it has boundary-induced phase transitions. So in this particular picture, I'm considering the special case where gamma, delta, and q are 0. So here you can indeed think of this as traffic on a one-way street. And the picture below has an alpha axis and a beta axis. So alpha and beta both range between 0 and 1. And you can see, it's kind of intuitive that if alpha is very large compared to beta, then we're going to have a high density of particles, whereas if alpha is quite small compared to beta, we're going to have a low density, and when alpha and beta are both large, we have a maximal current situation. Okay, so I also mentioned that this model was introduced by biologists. It's been cited as a model for sequence alignment, the nuclear pore complex, and translation in protein synthesis. I suppose everybody who's actually interested in biology is in a different session right now, so maybe I should just gloss over this, but anyway. Here's a picture I stole from the internet, which shows the translation in protein synthesis. I guess as I gather, there are these ribosomes that sort of go back and forth on strands of messenger RNA, reading the codons, and apparently there's sort of 3 steps. There's initiation, where the ribosomes sort of enter the lattice, and then there's the elongation, where they sort of go back and forth along the messenger RNA, and then there's termination, where they detach. So I think this is actually a sort of reasonable model, if this description is accurate. Okay, so now let me go back to the mathematics. So let me first again consider the case where gamma and delta are 0. So one would like to understand the stationary distribution of this Markov chain. Now that is the probability distribution that you obtain as t goes to infinity. Another way of saying that is that it's the left eigenvector u of the transition matrix with eigenvalue 1. Oh, it's a row vector. You've got a row vector and then a square matrix. Thanks. No, thank you. So here's the model when n is equal to 2 and gamma and delta are 0. And here's the transition matrix. So there's 4 different states. So this is a 4x4 matrix, and the rows and columns are labeled by the 4 different states. And so, for example, the fact that I have an alpha over 3 here means that the probability of going from hole to particle hole is alpha over 3, and every other entry is filled accordingly. And okay, I'm not going to do the computation, but in this case, our eigenvector is the following vector. So these 4 components represent the steady state probabilities. So the first one is the steady state probability of hole. This corresponds to the state hole particle. This is particle hole, and this is particle particle. And everything gets divided by a normalization factor in order to make probabilities add up to 1. Just to say a word about computational complexity, of course, in theory, one can always compute this left eigenvector of the transition matrix, but for a lattice of n sites, there are 2 to the n different states. So dealing with 2 to the n by 2 to the n matrices quickly gets very complicated. Okay, so now let me tell you how to answer the question instead using some sort of crazy-looking combinatorial objects. And I'll first state the theorem in a very vague way, and then I'll make it precise. So stating it in a very vague way, together with Cortiel, we found explicit combinatorial formulas for all steady-state probabilities using some tableau that we called staircase tableau, which are depicted in the middle of the picture. Okay, and I'm going to describe this first in the gamma equals delta equals 0 situation, just to make things simpler. So an alpha beta staircase tableau of size n is a Young diagram of this staircase shape, whose boxes are either empty or filled with alpha beta such that every box above an alpha is empty. So there's an alpha here, so everything above it is empty. All boxes left of a beta are empty. So the fact that there's a beta here means everything to its left is empty. Similarly there. And all boxes on the southeast border are non-empty. And then the type of the tableau is a word in particles and wholes. It's a state of the ASEP. And it's obtained by reading the southeast border and assigning a particle whenever I see a alpha, and a hole whenever I see a beta. And one way to think about this is that if you remember our picture, alpha governs the rate of particles hopping in at the left, and beta governs the rate of particles hopping out, or in other words, holes hopping in at the right. Okay, and so I haven't yet put in the parameter q, but now we'll do it as follows in a deterministic way. So q gets attached to every blank box, which has an alpha to its right and a beta below it. So for example, I have a q here because there's an alpha to its right, and it doesn't have to be adjacent, just to the right, the nearest non-empty guy is an alpha, and below it, the nearest non-empty guy is a beta. And then the weight of a tableau is the product of all boxes. Okay, so now I'm just going to define this normalization factor z sub n, and what we do is we write down all the tableau of size n, and we sum up their weights. And then the theorem is as follows. If we're interested in the ASEP with these parameters alpha, beta, and q general, and gamma and delta to be 0, then the steady state probability that the ASEP is in configuration sigma is precisely the following ratio, where at the top I look at all tableau of type sigma. So sigma is a word in particles and wholes. It's exactly the configuration I'm interested in. And so what I do is I write down all the tableau with the border being in an alpha and beta, having alpha and beta according to that configuration. And I sum that up, and then I divide by the normalization factor. Okay, so I'll just show the very simplest example, non-trivial example, when n equals 2. Okay, so what I want to do is write down the tableau of the different types. So suppose I'm interested in the probability of state particle-particle, car-car. Then what I do is I need to put alpha-alpha in the diagonal boxes, but according to our rule, alpha forces everything above it to be empty. So there's only one tableau like this. Now on the other hand, suppose I'm interested in the state particle hole, then I need to fill along the border an alpha and then a beta, but since alpha forces everything above it to be empty and beta forces everything left to be empty, I have complete freedom as to what goes in this box. So I could put an alpha here, or a beta here, or I could leave it empty, in which case it needs to have a q. So there's 3 tableaux of this type. And if I'm interested in the state whole particle, then there's 1 tableau like this. And if I'm interested in the state whole, there's 1 tableau like this. Z sub 2 is the sum of the weights of all of these tableaux. So this alpha squared came from here. This corresponds to this term. This tableau corresponds to this term. This tableau corresponds to this term. This alpha beta gives rise to this. And this tableau gives rise to this beta squared. And now by the theorem, this allows us to compute all of our probabilities. So the probability of particle-particle is alpha squared, exactly what we get from that tableau. The probability of particle-whole is the sum of these three monomials. The probability of whole particle comes from this monomial, and the probability of whole-whole comes from this tableau here. Okay, is that clear? Okay, so that was a sort of toy example when gamma and delta is 0, but I just want to point out that that condition, that gamma and delta is 0, is not necessary. We just add gammas and deltas to our tableau in a not very surprising way. So the general definition of a staircase tableau is a Young diagram of that staircase shape, and now boxes are empty or filled with alpha, beta, gamma, delta, such that anything above an alpha or a gamma is empty. Every box to the left of a beta or a delta is empty, and all boxes on the southeast border are non-empty. And now the type of the tableau is a word in particles and wholes obtained by reading that southeast border. And whenever I see a gamma or a beta, I put a whole, and whenever I see an alpha or a delta, I put a particle. And alpha and deltas were rates of particles hopping into the lattice, whereas betas and gammas were rates of particles hopping out, or in other words, holes hopping in. And then I'm not going to give you the local rule, but there is a local rule for putting in Q's. And then the weight of a tableau is now the product of all boxes. And then the theorem is the same as before. We introduce a normalization factor by summing over all tableaux of size n. And now in the general version of the ASEP, where the parameters are all arbitrary, the steady state probability that the ASEP is in configuration sigma is again this ratio where the numerator is the sum over the weights of all tableaux of that type sigma, where sigma is exactly the configuration of particles we're interested in. Okay, so I'm sort of pulling crazy combinatorics out of thin air, and it's probably not very intuitive. Actually, it wasn't intuitive to us either, but I just want to give a hint as to where sort of crazy combinatorial objects sometimes come from. So in 2005, I was studying the positive Grassmannian using some kind of tableau called Lie diagrams that don't look at all like the ones I've just shown you. And I wound up, in the process of enumerating cells, writing down a polynomial that counted cells. And this was introduced purely for understanding the positive Grassmannian. But 2 years later, Courtiel proved an interpretation of that Grassmannian polynomial in terms of the ASEP. So she actually interpreted this polynomial as giving the steady state probability that the ASEP on n sites is in a configuration with exactly k particles. So.
You said are these fields separate until now? Or
Yeah, right. Right, there was no connection whatsoever between positive Grassmannian and ASEP, and it's still sort of kind of a mystery as to why. So I wrote down these polynomials and pointed out they had nice combinatorial properties. They generalized some famous combinatorial numbers. And then she was looking at the ASEP, and she knew her whatever polynomial she was looking for had to specialize to some Neriana numbers and whatever binomial coefficients. And she asked around and said, do you know any polynomials like that? And somebody pointed her to my paper. And so it's sort of a nice accident that this happened. And then we started trying to generalize that correspondence. And via a series of bijections, we got from Lie diagrams to these to first of all a more general case with alphas and betas, and then to the staircase tableau, which solved the general problem. So it was kind of a series of accidents. Well, not exactly, but. Okay. So, so there's actually an important generalization of the ASEP with several kinds of particles. So here we have two kinds of particles. There's heavy ones and light ones. So black is a heavy particle, gray is a light one, and blank boxes are holes. And you can write down this model in a very natural way, where in the presence of holes, both light and heavy particles behave as do normal particles. And if you put a heavy particle and light particle side by side, the heavy particle behaves like a particle and the light particle behaves as a hole. So this is a kind of very natural extension. And one can analyze this model as well. So in work with Kortila and also my student Olia Mandelstam, who's here, we generalized the previous formulas using some kind of rhombic tableau, which now look like sort of three-dimensional figures. And an important step in a special case was made by Mandelstam and Viennot. So I'm not going to give you definitions, but I just will show you a picture of what these kind of generalized 3D objects look like.
Is there a version of the Grassmanni for these pictures?
I would like to know. I would like to know. Even in the gamma and delta case, I don't know if there's a version of the Grassmannian, but maybe some kind of double Grassmannian. Okay, so now sort of three-dimensional combinatorial objects, but same flavor of results as before. Okay, so now I want to mention a completely different connection, which is to orthogonal polynomials. So let me just remind people what are orthogonal polynomials. So let's choose some measure mu, and we say that some family of polynomials, p sub k of x, is orthogonal if, when you integrate the product of two different ones against the measure, you get 0. And now, given such a measure, or such a family of polynomials, we define the nth moment to be what you get when you integrate x to the n. And that's kind of a natural object in that if you understand how to integrate x to the n for all n, then you know how to integrate all polynomials. So these polynomials are kind of classical objects. There's a famous text of Askey and Wilson from maybe 1980 where they're studying the different families of orthogonal polynomials in one variable. And there's a diagram much like this in the very back of the book, except they didn't use their names at the top. There was they put something else there, but the polynomials at the very top have since been renamed Askey-Wilson. So what this diagram is showing is how these different one-variable orthogonal polynomials are related. And whenever you see an arrow, that means there's either a specialization or a limit that gets you from one family to the other. And so the combinatorics of these orthogonal polynomials was studied quite intensively by many mathematicians, including some of these people here, trying to work out formulas for both the polynomials and for their moments. But they really had no results at all for Askey-Wilson. Now in 2005, actually, 3 physicists, Uchiyama, Sasamoto, and Wadati, discovered a close link between the ASEP and the Askey-Wilson moments. And so that kind of gave people the hope that if one completely understood the ASEP, one would completely understand combinatorially the Askey-Wilson polynomials and moments as well. Okay, and that's true. So using the combinatorial tableau that we had to study the ASEP, we were also able to give the formula for these Askey-Wilson moments in terms of those tableaux. So we have a kind of triangle of relationships here. So that top arrow between ASEP and Askey-Wilson was discovered by Uchiyama, Sasamoto, and Wadati. Okay, now one can keep generalizing everything. So why stop at one variable? So it was pointed out to us by various people that Askey-Wilson polynomials are the one-variable case of Koornwinder polynomials, which are also known as Macdonald polynomials of the root system BC. And And these polynomials have connections to algebraic geometry and representation theory, so they're very important. And a question, basically, that we were asked was, can one sort of generalize this trio of relationships where you replace Askey-Wilson by Koornwinder? But for a long time, we weren't quite sure what to do because first, it wasn't quite clear how to define the Koornwinder moments. It wasn't clear how one should generalize the ASEP. There's many ways, a priori, to generalize it, and it wasn't clear how to generalize the combinatorial objects. But it turns out that the two-species ASEP, which I showed, is the right version of the ASEP, and then the rhombic tableau were invented for the purpose of understanding both the two-species ASEP and the Koornwinder moments. Uh-huh.
So you mentioned Macdonald-Polynomials of type BC.
Yes.
You mentioned Macdonald-Polynomials of type BC and also Grassmannians. Is there a direct connection in your mind that is related to this story?
Not at the moment, but I think there should be one. Yeah. But there's no direct link right now. So I was just going to say that, so this trio gets replaced precisely with these three objects, two-species ASEP, Koornwinder, and rhombic tableau. So now I just say a few words about next steps. So the Koornwinder moments are actually specializations of certain Koornwinder polynomials. And I mentioned the Koornwinder polynomials are type BC Macdonald polynomials. Now the type A have been studied quite a lot, and there's a lot of amazing work, including Heyman's work on the n factorial conjecture, connections to the Hilbert scheme, explicit formulas, etc. And so far, almost nothing for Koornwinder. But one would like to develop all of the combinatorics in geometry, because one reason is that the Macdonald polynomials of any classical root system are limits or special cases of Koornwinder polynomials. So a long-term or medium-term goal is to completely understand those polynomials from a combinatorial point of view, maybe extend the particle model interpretation and relate it to geometry. So thanks very much.
So questions are in order. There's one.
Yeah. I don't know much about the subject, but there's something like similar, something of similar flavor, like beta ansatz, XXZ model. Is it all related? I suppose.
Yes. Yeah.
Razumov-Stroganov conjecture. Is it?
Yeah. Right. So so there's a very, very close connection between the ASEP and the XXZ model. I mean, they are almost the same. Yeah.
So you mentioned a very brief
Wait.
You made a very brief remark about the complexity. So do your formulas give polynomial time algorithms for evaluating the stationary distribution?
Yeah, I would say, I would say so. One can encode the tableau using some matrices and reduce everything to a problem of matrix multiplication. Now, the matrices actually are infinite by infinite, but if you're only interested in the lattice size n, then you only need sort of n plus 1 by n plus 1.
I noticed that the terminology is similar to what's used in semiconductor physics. Does the ASEP model have applications there?
Oh, I have no idea.
Okay.
So I know that Alexei Borodin has also worked on these Macdonald polynomials in the context of the ASEP. So what's the connection between your work?
So that's a really good question. So Borodin and Koornwinder have these Macdonald processes, and they've related them to the ASEP. Now, their Macdonald processes, at least as of the moment, are in type A, and the ASEP that they look at doesn't have open boundaries. It's on an infinite lattice, and so I don't know how to make a precise connection, but it really feels like there should be one.
So sort of as a follow-up, in that work, when you take the continuum limit, continuum space limit, you get certain processes related to random matrices. Is there some similar interpretation in this case?
I think there should be, but I don't know offhand. Yeah.
Good. If there are no more questions, let's thank Lauren.